All right, good morning, everyone. I said my name is Julio Belmonte. I'm a former PhD student from James Glacier, and I have my own lab group at NC State University. And today I'll be talking to you about cell compartments on module 5.1. Again, this is going to be recorded on Zoom and shared on YouTube. So let's get started. Okay, so what I'll be talking today will be I'll start with the motivation about why you want to use cell compartments in CompuCell3D. Okay, then I'll talk about different ways to think about it, functional versus structural heterogeneity in some regions. I'll talk a lot about internal versus external contact energies. And then we do have two exercises, one to create a cell with a nucleus, membrane, cytoplasm, and that to be built up on the cell crawling model that you have seen before. And the other one, you're gonna create an epithelium in CompuCell3D, which has an apical, basal, and a core compartment. And all this comes down to be an exercise on choosing the correct contact energies between your different cells, different components of the cell. Okay, so many things on CompuCell3D relies on that choice, and I want to walk you through how to make good choice of these contact energies. That's one of the crucial things to learn how to do in CompuCell. So let's talk about why you want to make great cell compartments in CompuCell3D. So first of all, the reason is that the real cells, they're not just a bag of homogeneous bag of liquid that just kind of floats around usually, or initial cell models. The cell is completely heterogeneous. You may add a force that make it move to one side or to other side. The cells see other cells, but otherwise are cells that we create in CompuCell3D, and also in any other cell models. Like if you're using a vertex model, self-centered model, or any other type of model, is usually assume that the cells are completely homogeneous, right? They have no internal structures. But the reality is that the cells have lots of internal structures, right? They have a nucleus, they have a cytoplasm, they have a Golgi apparatus on one side, the actin cytoskeleton may be more enriched on one side than versus the other. If the cells are crawling, there's a clear front and an end, right? Sometimes the ends it has a very long tail, as you see in this picture here, or just contracting and helping the cell to move forward. And if the cells are in an epithelium, right, then they have a very well structured components. They have an apical side, the basal side, the sides they have the on the lateral side where they actually make the desmos zones and the addition junctions. So the cells, if you want to get a little bit more complicated, you have to take into account the fact that the cells have spatial heterogeneities, and maybe it's better to make our CompuCell models a little bit more um, sophisticated to actually account for the internal spatial heterogeneities inside the cell. Okay, so and that is something that cellular POTS models in general have a great advantage of the other models, because it's very easy to put them in that. You can use the concept of a generalized of a cluster cell, which I'll talk about later, and you don't have to make special rules for that. You don't have to kind of keep track of exactly what those cells are and who they belong to. And that's not easy, something easy to do with the other agent-based models. A point model or vertex model is very hard to do, but in the cellular POTS model, that's easy to do. And you can even go further and make them actually very dynamic compartments, which are going to be the topic, an advanced topic for next week. So before you go that, what am I talking about when I tell you about a CompuCell model with compartments? That's what they would look like. Okay, so here you see two pictures. Okay, two examples of how to use cell compartments in CompuCell3D. The top one is a more uh, uh, structural compartmentalization of the cell. So here, each one of the cell compartments is actually matched to a specific organelle in your cell. So here we have in green, we have the membrane as defined as cell type. You have the cytoplasm of the cell, which you see in yellow, and then you have the nucleus defined as in green, sorry, blue. And you can have other compartments that actually map up to a specific organelle in your cell. You can have the mitochondria, you can have something else that is more important for your, you can have the vacuole, and you can add each one of cells different cell type that you put inside your cell. Okay. And the other way that you can also use compartments is not by a direct matching between a cell organelle or cell structure, but you can maybe a little bit more abstract, and you can define a region of the cell that's actually a collection of many proteins and many organelles, or even diffusing proteins that just get localized one side of the cell versus the other side of the cell. And that's what you see here on panel B, where you have an epithelium. So that makes a two-dimensional epithelium here. Of course, you only see one is a two-dimensional simulation, so you only see a line here. And here in blue, you have the apical region of the cell. In green, you have the basal region of the cell that touches the ECM. And in red, you have the core of the cell or the lateral compartments of the cell. So in this example, the apical, the core, and the basal, they are not well-defined structures in the cell. You're just kind of abstracting. But you know that your cells, when they are lying in epithelium, right, they become apically basal polarized, and they should have different properties. So the apical cell side of the cells, they usually are more contractile. They like to face the medium, and they are a little bit more soft. The basal side of the cells, they like to face the EC extracellular matrix. Okay, they're tightly. They have integrins that attach to the ECM, and the middle core of the cell or the lateral cell of the cell, it's actually usually where the cells actually connect to each other along the epithelial, so they'll have a higher, you expect them to have a tight junctions between the neighboring cells, so you probably have a higher adhesion between the core and core compartment than we have between apical and basal compartments between the cells. So that are the two ways that you can think about that, and whatever you're gonna do something that looks like this or something like that, it really depends uh, on the type of application that you want to have in your simulations, okay? So just a little bit of, and in this talk here, you're going to be doing both of them, okay? So just give a little bit of history. The idea of using cell compartments was something that was first using in cellular pots model to model myxobacteria by the group of Andreas Dauch and Starros and Peruani, which you can see that the cells are made of, that's a mix of bacteria, and then the cells have a front and a tail and a lot of spatial bodies in between, okay? And there's another application here where you use the concept of cell apical basal, and that was done by Dr. Abbas Shirinfrat from St. Jude's Hospital, but at the time he was a James group, and then he used that to model lens formation. So the basal sides here, they become bigger, and then this one contract, and then that leads to a cup formation, okay? So this is two very early applications of the use of cell compartments that was done. So this was about 2010, this 2007. Okay, but even ever since then, they have been used more and can make it a little bit more sophisticated. So this is another use of cell compartments for renal tube, and the cells have a apical, basal, a core, and also a lateral compartment, and they can live by themselves, and then all this is fixed. They can also live in epithelium, and it can in this model they actually can the cells can grow and make cysts or a very big cyst, a very small cyst. And you can also use the cell compartments to actually make some compartments that are not fixed in space, but are very dynamic. And this can be used, for example, to model the emergence of planar cell polarity and tissue alignment along the plane of the epithelium. So that's an example where we use the idea of cell compartments and let the compartments sort themselves out according to the contact energies. And over time, the cells rearranged the compartments and found a direction, and they all polarize along a given direction. But that's a little bit more advanced topic that we'll be covering more in details on next week. But If you're interested in pronunciation polarity, it's going to be a guest talk today by my student Abisha Tayamba on the third session. So as a little bit of advertisement, you can check that out. Okay. All right. So that's just the motivation and give a taste of what you'll be able to do later by the end of this workshop. But let's start with using cells as with structural compartments. So here's the example I gave before, a resting cell which has the membrane, the cytoplasm nucleus. So that's one way uh, to model them. And this is the example that you have seen yesterday of a crawling cell that was introduced by Gilberto. And here, of course, you have a different problem. So you have a different way to compartmentalize your cells. So here we still have the nucleus, but we have now the cytoplasm and uh, instead of have the membrane, you are modeling the lamellipodium, which is going to make the front of the cell. And in this model here that's being used today, that's how it works. That's what you probably have done yesterday, or at least download the simulation to play with it. Uh, these are the three compartments. We have a lamellipodium, a cytoplasm, and a nucleus. And the way that the cells move is that you add the external potential force on the lamellipodium, which is line about the direction between the nucleus and the lamellipodium. So you add a force there, the nucleus tends to stay behind. So that leads to this shape, and the direction of the force that you add to the lamellipodium changes every a given number of steps. So that's why the cells move on one side and on another side and another side. So that is how it works. So you have already seen this before, okay? And when you did this model, at any time, there was no need to invoke the idea of cell compartments because you're only having one cell. But I can ask you here now, what happens if you just try to have two cells? Would the model still be well behaved or not? Uh, so, well, you may think that it's going to just be very well as good as before, but when you start to do this two cells, at first they seems to be okay. There you see no problem. However, if you wait a little bit long, oops, what happened here? Okay. What happened here is that the two cells kind of merge and one of the lamellipodia just flew away. Okay. Uh, and if you, of course, if you do that with four cells, okay, at the very beginning when they don't see each other, everything looks so fine, and eventually things becomes very bad. Okay. And okay, and do you guys have any idea why this happens? Well, the problem here is that when I start simulation like this or here, okay, it's very clear that this nucleus belong and this cytoplasm and this lamellipodium belong to this cell, and that this nucleus, this cytoplasm, and this lamellipodium belong to this cell, so on and so forth. But once they see each other, they cannot tell apart who belongs to whom. And then what happens is that, okay, if this nucleus belong to, should go to this cytoplasm or that cytoplasm? You do not know. Yeah, exactly. Similar contact energy of the same parts of the cell. They exactly have the same energies, right? So what the nucleus know? The nucleus know that it wants to be inside the cytoplasm. And now if when you see two cytoplasms, oh, that's great. They're going to be inside both, right? It does not know that it belongs to one cell or the other. So that you have to compartmentalize which the cell somehow, okay? So the problem here is exactly that, right? There's no information on your contact energy about who belongs to whom, right? They probably should have different energies when they belong to the same cell and then when they belong to the different cell, okay? Or so what you have to do, you have to, how you can differentiate that? Well, you differentiate that by introducing the concept of cell clusters or cluster of compartments that belong together against another cluster of compartments that belong to another cell. Okay, so uh, uh, so let's define exactly what you mean by clusters, okay? So what is a cluster in this concept of cellular POTS model, okay? A cluster is a collection of cell compartments that belong to the same cell, okay? So in order for the cells to not mix, we need to distinguish between what belongs to one cell, or belongs to another cell, or what belongs to one cluster to what belongs to another cluster, right? So how you do this in CompuCell3D, okay? So in cellular POTS model, you know that each cell here, when I show this picture, you have the nucleus and membrane and cytoplasm are different compartment types. When I show that, I have apical, central, and basal as different compartment types. But in order for this to work, what I have to tell is that all these compartments here that on top of another belongs to one cluster, and all these other ones belong to a different cluster. So this is done by introduce the idea, the extra number that's going to tell which cells belong to the same cluster and which cells belong to another cluster. So the cells themselves, they have an ID 1, 2, 3, 4, 5, 6, which are unique to the cells. But on top of that, you add a second ID to the cell, which is going to tell the family of cluster that they belong to. So we have a cluster ID, okay, which is 1, 1, and 1 for all those cells, and a cluster ID 2, which is 2, 2, 2 for all those other cells. So that's how it's done. Okay, so let's just go back a little bit uh, to to remind yourselves exactly how this is done, right? So let's step back and kind of do a revisit of how the cellular POTS model works. Okay, so each cell is the final collection of sites or pixels in a lattice grid, which share a unique number or cell ID. So here you have cell one that occupies all these places, cell two that occupies all these pixels, and cell three that occupy all these pixels or voxels, right? And on top of that, each cell ID has also another number which tells its cell type. So uh, ID 1 is type A, ID 3 is also type A, and ID 2 is type 2, okay? But they're all different cells, okay? They have different types. They can have the same type, but they all have this unique ID, okay? Now, if you want now to group different IDs into cluster, you have to give the cluster ID, okay? And that's what's done in this picture here, okay? And here you have a group of cells 1, 2, 3, IDs 1, 2, 3, and a group of cells with ID 4, 5, 6. And on top of that, I also assigned in a cluster ID that's going to group all those cells into one cluster and then group all those other cells in another cluster. So you see that here you have two cells, right, or two clusters, one in red and the one outlined in blue. And the first cluster, you have a cell with two compartments. One has ID 1 of type A and has cluster ID 1. The other has ID 2 is of type B, but it also has a cluster ID 1. The other has ID 3 is of type C, which is the blue one, but it also have the cluster ID 1. So because they all have the same cluster ID, they are form one cluster of cells or one cluster or one uh, um, cell. And the second one in blue, it has the same thing. Each one of those things that have exist in the grid, they have this own unique cell ID, 4, 5, 6. On top of that, they have different types. So these have type A, type B, type C. But what they all share in common is a cluster ID number, which in this case is 2. So that's how you define those two to actually belong to different cells and not belong to the same cell. Is this making sense how that works in the cellular POTS model? If it does, give a thumbs up or say yes in the chat. If it's a little bit confusing, please send a message and I'll try to expand here. Okay, good question, Eudes. Well, whether they belong to the same cell or not, it really depends on your interpretation on your model, right? So here we usually say that we assign a cluster ID to grab all the compartments and say that this is a simulated cell, okay? So in this case, you have each cell gonna have three compartments. The cells can have just two compartments or one compartment, or they can have 5 or 10 compartments, depending on how much details you want to put in your model. But usually, the way people use a compartment is that a cluster ID defines a single cell. Okay, you might have another situations that maybe your all compartments that share this cluster ID may be a collection of cells. It can be a tissue, right? And each or maybe you can even use the cluster ID to be an internal part of the cell that has same properties. Uh, you can use the concept of the cluster of clusterization to cluster wherever you want and call it whatever you want. Uh, maybe you can use one cluster, maybe have two um, collection of cells that belong to different tissues, right? And you put them together, but they also all have uh, their own cells, which should have their own energies, but they because they belong to tissue, they have a slightly different energies when they contact each other. So maybe you can also cluster ideas to differentiate between whole clusters. But usually, a cluster ID is a representation of one biological cell with many internal compartments inside. So the problem that is CompuCell3D is uh, more agnostic about exactly how you interpret it, but you can use that to do different things. But for simplicity, in this model, a cluster ID is usually a cell with different types of compartments inside it. Okay. And the other thing you can have is that maybe your cell should have two nuclei, right? So you can have a compartment cell actually with two nuclei cell types inside it, okay? So there's no rule that you can have only a compartment of each type, one compartment of each type inside the cell. You can have a cell with multiple compartments of the same type. Okay, so in some cases, for example, you want to model a multinucleated cell, so you can have a cell cluster ID with 2 or 3 or 4 or 5 nuclear compartments inside. That's something that you also can do. All right, so now, so what you want, going back to your cell migration model, we want to put now two migrating cells, okay? Each migrating cell should have three compartments, a nucleus, a cytoplasm, and a lamellipodium, okay? And this is how we'll be doing. To really differentiate between one cell and the other, we're gonna assign a cluster ID to them, okay? So this cells here, okay, they have a nuclei, cytoplasm, and a lamellipodia. They have cell IDs 24, 32, 43. The cell IDs can be any number of it, but they all have the same cluster ID 2, which makes them a single cluster. And all those compartments here, they have their own type that you see as in the by the color. They have their own cell ID 59, 88, 85. But what grouped them together is that they all have to share the same cluster ID. In this case, is cluster ID 10, okay? And so these have a cluster ID 10, cluster ID 10, cluster ID 10, so which tells you that they are belong to the same cluster of cells, okay? So here I'm using kind of more or less random numbers to show that there's no need for the cluster ID to match any cell ID inside the cell. And exactly which number you use doesn't matter as long as this cluster ID is different than this cluster ID. Because if you make all this cluster ID to be also two, then they will all belong to the same cell. Then you group them together, okay? If you give a different, then they're going to be treated as different cells. Okay, so that's what you'll be doing in our model. But before you do that, let's now talk about uh, exactly where the cluster ID comes into play to actually make the cells look different, okay? So in order for the cells to not mix, right, we already distinguish which one belongs to each one, to each cluster by assigning cluster ID. But on top of that, what you have to do now, you have to differentiate the contact energies between compartments that belong to the same cluster and contacts that belong to different cluster, okay? So which means that now you should need to have two different contact energies. One for the external for the cells that have different cluster IDs, and that's going to be our original contact energies, okay? And we also now need to specify a new set of contact energies for the cells that belong to the same cluster. And that will be now the internal contact energies that you see here. So when you do a model with cell compartments, okay, you now need to specify these internal energies of the compartments, okay? Uh, so which means that originally this CompuCell3D already assumed that all the cells belong to have different its own cluster ID. So your contact energy that you see in your cell simulation is usually the external contact energy. And when you use compartments, you have to specify the internal contact energies. Okay. So again, the internal contact energies sets the energy between internal compartments. So between this one and this one, this one and this one, and the lamellipodium and the nuclei. So that's the ones you'll be specifying here. And for this cell crawling model, right, we can use the original values that you have on the model that you have seen the crawling cell. So because when Gilberto made that crawling cell model, he was assumed that you have only one cell. So the energy that he used there should be now go to the internal contact energy matrix of energies. Okay. And these values here in the diagonal, cytoplasm, lamellipodium, nuclei, you don't need to specify because in this specific model, each cell has one each compartment has its own type. And so there is no two nuclei, there's no two cytoplasms, just no lamellipodium, so you don't need to specify those energies here. So you're all set for the internal contact energies. Now, the external contact energy or the regional contact energy that you see in our XML, okay, set the contact energy between external compartments, okay? So by definition, everything that outside compartments contact with the medium is always an external compartment that does not belong to any cell. So by definition, the contact with medium and all compartments is external. So here you can just copy the values that we use for the cell crawling model, which is here. But all these other energies here are set the energies between compartments that belong to different cells. So that should be the nuclei and the nuclei, cytoplasm belongs to cell, and lamellipodium that belongs to a different cell, and all the cross terms. So this, for example, C and L here going to be the energy between the cytoplasm belongs to one cell and the lamellipodium that belongs to a different cell. Okay, so this one here you have to choose what values you want to use. So so do you guys have any idea of what should be the values that you'll be using here? Should they be very high or should they be very low? Should they be higher than these values here or should they be lower than these values here? I want to hear your opinion in the chat. So remember that we don't want the cells to mix when they belong to different clusters, right? Yes. So yeah, so they should high, so it should not mix. You're exactly right. Okay. So usually a rule of thumb is that the external contact energy should usually be higher than the internal contact energies. The internal contact energies usually have to be lower because you want them to actually group together and belong to the same cell. And everything that's external energy, they should be higher, so they will not mix one another, they'll actually stay separated. Okay. So we can start to reason out what each one of those values should be. Okay, so if you go now about the nuclei, okay, well, the nuclei not only cannot mix with a cell, it cannot even leave the inside of the crawling cell because it has to really be inside. So you want these values to be very, very high. Okay, so I have high here in bold. And these other ones, okay, well, the nuclei, the cytoplasm and the lamellipodium, it's okay if they touch the other cell as long as they do not go inside. So this you also want to be high, but it doesn't need to be as high as the external contact of the nuclei with the other cells. So you also be high, but doesn't need to be as high as before. Does it make sense? So here I'm saying that the nuclei should never touch the other cells, but it's okay for these other two to actually touch the other cell, but they should not mix. So they should still be high, but there's no need to be that high. Does it make sense? Okay. So that is how you should think about the energies. And every time you choose the energies that you should put on the contact energies on your system, even if you're not using internal compartments, you should think about what should be, which const should be favorable, which const should not be favorable, and which const should be completely forbidden. So you should first make the hierarchy of contact energies, and then you add the numbers on top of that. Okay. So with that, let's go to your first exercise, okay, where you're going to start to implement the model that you see here, okay, where you have one cell, uh, that's crawling cell, and it actually can grow, it can divide, it can make multiple cells, but you have to set up the energy in such a way that they will be well behaved like this. You have multiple crawling cells, but they do not mix with one another, okay? So we have to use the contact energy, specify that all the parts belong to the same cell. We're going to implement the energies, implement cluster division, and then as soon as you have two cells, you have to choose appropriate values for the contact and internal contact energies. Okay, so let's start with this and start with that one. And for this exercise, I want you download the cell crawling model from yesterday, and I make a new version of it, and it's on the model version. You should download the 5.11a.zip. Please download your computer, unzip, and open it and tweak it, and I can walk you through what you should be doing. So I'll give you a minute to do that, and let me know if you have any questions in the meantime. Okay, so I assume that most of you have already downloaded, okay, and open to it. So for this exercise, I post, you have all the versions there, 5.1 A, B, C, D. The D is going to be how your file should look like at the end of the exercise. So you have everything there. So you have two choices here. You can either code along, okay, or you can just pay attention and follow the slides. But by the end, you still have all the code there for you, okay? So for those one that have downloaded on the open tweet it, okay, this is what you be seeing. We should open, and if uh, you can open it and can run, and what you should see is something that looks like this. Should see is basically you see the cell model that you have seen yesterday from Gilberto, okay? And the code is exactly or very similar to what he had yesterday. And you should be seeing a cell that is happily crawling around, okay? Now you want to modify this code, okay? And the first thing you want to do is you want to add the content internal plugin, okay? So to do this, I want to have the XML open, and I want you to go to line 53 or make a new line on line 53. And once you are on line 53, I want you to go to CompuCell3D ML, plugins, and select Contact Internal. And when you do that, click, okay, and then it's gonna add the plugin of Contact Internal plugin for you, okay. So please do this. I'm not sure that you really need to do line 53 in the new version of Tweedit, but just go to line 53. Once you are on that line, menu, plugins, contact internal. So if you get there, you should, if you have an older version of Tweedit or CompuCell3D, you should just see the code paste for you. But if you have the 4.9, you actually should see a pop-up screen. Okay. If you see a pop-up screen, it will look like this, okay? Uh, which is asking, already showing the two contact energy tables, right? And ask you to write the values there. When you do this ContactInternal plugin on line 53 XML plugins ContactInternal, you're going to see this pop-up in window, which you can already add all the energy that you want. We do not want to work on them yet. Just hit OK, okay, and proceed, and you should see this kind of code in your code. It should be 5.11a underscore new, and that one that should not be growing and dividing, okay? Yes, the movement of the cells are random, okay? And the logic is the one that Gilberto has explained. 5.1.1a underscore new 2.zip. That is the definitive version that you should be starting with. If you already opened the new, it's okay. You can do that. It's just have a step that is already there for you. But please, if you can, spend 30 seconds, download the new zip, unzipping that, and open that in the folder. Okay. So this new version should be exactly what you see here. It should behave like this: a single cell that does not divide and is moving more or less like you see it here. Okay, so it looks good to Kyle. Thank you. It looks good to Ali. Excellent. For Ilts, the let me put the speed detach it. It can happen, okay? But if you just try it again, maybe it will not happen. So that may happen. Okay. All right. So does everybody has a code that kind of works properly? Now that everybody has the correct starting code, let's revise what you want to do. Okay. We have to, I want you to all to go to the XML file. Okay. Go to line 53, go to CompuCell3D plugins, contact internal. When you click that, you should all see a pop-up window. Okay. Which gives the opportunity to add these new contact energies. I don't want you to do that right now. I just want to hit OK, right? And your code should looks like this after you do it, okay? Yeah, so that's a good question. I do not know why the old contact plugin gets commented and a new one is put. I guess it's because the pop-up window that appears is just comment the old one and create a new one with what values you put on the pop-up window. Yes, I agree that it would be clean if that the contact energy was just made be kept as it was before, but that's the how it's working right now. Okay. Okay, that may be yes, please. So that's one of the next things I want you to do. Well, you can already set up the neighboring order to be 4 instead of 2. We're going to do that later, but you're going to do this right now. Yes. That you probably help with the detachment of the Lamellipodium from the nucleus, from the cytoplasm. So you should have something here. You feel free to already change this neighboring order from 2 to 4. When you change the neighbor order, yeah, it does change the relative weight of all these values here. And notice that the out internal contact energies are 10 by default. We're going to change that later, okay? So if everybody got here, okay, now you have the two different contact energy matrices, one for the external energies and another for internal energies, right? But if you just run your code as it is, save and run your code as it is, you still see the exact same result because all the cells we have not tell that those three compartments that you start with should belong to the same cluster. So that's what we're doing now. We're gonna do this part B of the code, which is gonna specify that the initial compartments belong to the same cluster. Okay. Now to do that, we have to go into the steppable files Python. Okay. And in there, I want you to see this code here, where at the start function, where you go over all the cells and you give them the volume and the lambda volume, okay? In this part, what you want to do, you want to grab what is the cluster ID of the cytoplasm, okay? And assign this to be also for the Lamellipodium to have the same cluster ID and the nucleus to have the same cluster ID. So that's what we'll be doing, okay? So please, I'll go to steppable files and go to this line. And what you now do, you're gonna make a new line after line 14, okay? So in between here, you have to make a new line and you're gonna grab the cluster ID of that cell. To do that, you go to CompuCell3D Python, cell attributes, and you click on cluster ID. And after you do this, you should get this new line of code here, which is where you store what the cluster ID of that the cytoplasm is. Yes, excellent. Okay. Uh, One thing that you can do when you click on CompuCell3D Python, there should be an option at the end that says skip comments. Okay, if you click that, you get rid of the read on access and all the spaces. But basically, Ali, you did what was supposed to do. Yes, that's exactly how it looks like. Should look like. Yes. So now we got the cluster ID of cytoplasm, and what you want to do now, you want to assign this cluster ID number to the Lamellipodium and the nuclei. So to do that, you're gonna make a new line here and another new line here where you do one at a time, okay? And once you make that new line, you do again CompuCell3D Python, cell attributes, and you select cluster ID reassignment, okay? And when you click cluster ID reassignment, you're gonna should give a new lines that looks like this, okay? Self-reassigned cluster ID cell. But instead of having cluster ID here, it's gonna just have a random number. I think it's 1500 something, okay? Uh, but instead of using that random number that the code gives you, you just substitute that number by this variable that you got here. So that means that this cell here with Lamellipodium will now have a new cluster ID, which is going to be exactly the same as the cytoplasm. And you do the same thing for the nuclei. And after that, now all those three compartments have the same cluster ID, therefore they belong to the same model cell. Does that make sense? Who got here? Yes, almost there, Ali. What you have to now, you have to substitute this 1536 by cluster ID. So right now you have a number here. Instead of this number, you want to have the cluster ID variable. Excellent. If you got this far, please hit save and play your simulation and tell me what it looks like. So yeah, everybody got here, please say yes in the chat so I know how you're going. All right, so if you save and play, okay, so again, there are the lines, the comments. You get something that maybe look like this, okay, which does not look right, very right, okay. You see the nuclei is kind of stretched behind and the lamellipodium is all around the cell, okay. Yeah, good comment by Prion. That works. That code here works because we have just one compartment each type. Uh, if but it's okay for now. So you may have got something that looks like this with the nucleopod all around the cell, the nuclei in the back, right? And the reason that is looking like this is because we have not made any change in the new contact internal contact energy matrix that we had before. Okay. So let's now fix that, okay? Or before you go to the code to fix that, let's take a look at these contact energies, okay? So this is the contact energy that you had before, okay? That you just inherit from Gilberto's code with 22, 10, and 100 with the contact of the medium, and you have these internal ones. But when you paste your new code, contact energies in your XML code, it just had all the values set to 10, okay, automatically. So what you want to do now, you want to change your contact energy from 10, 10, 10 to exactly the same energy that you have in external energy. Okay. So I want to copy this into this. So this should be 11, 10, and 40 in the internal contact energy matrix. So I want to do this. And here what you're going to do. So that's how your code look now. Right now, all those values here are 10 by default. So that's what the 3D is going to do for you. I want you now to copy these areas into here. And while you're doing that, you also want to change the neighbor order that you had before. That was 2. I want to change it to 4. So many of you had already done that. Okay. So please do that. And once you do this energy, save and play, you should see back again a well-behaved crawling cell. So please copy those energies from here to here. Okay, so this should be 11, this stays as 10, and this should be 40. Okay, save, play, and tell me if you got it. And uh, let me know in the chat if you when you complete this. Okay, excellent. Nathaniel got back a well-behaved crawling cell. Okay, Kyle looks good. Does it look good for everyone? What? Oh, excellent, Ali. So Karen asked, what exactly does the neighbor order do? Okay, the neighboring order, um, every time you do a lattice copy attempt, okay, that lattice that's being copied and change type, okay, it has an energy with all the neighboring lattice sites around it, okay, and this neighbor order, you tell you how long, how big you make this that lattice site sees the other lattice sites, and how much that you're going to influence the energy of that specific lattice site, okay, with respect to neighbors, okay. So if you make a neighbor order of 0, it doesn't see the neighbors. If you make a neighbor order of 1, you only see the pixels that are right above or uh, below it or left or right. If you make a neighboring order of 2, it makes a little bigger place. If you make a neighbor of 4, it's big 4. You make a neighbor order 7, 10, it gets bigger. Okay, so that's basically sets the weight of your contact internal energy in the behavior of your cells. So yeah, so it sets how far the cells can sense each other. Oh, excellent. Kyle put a picture there. Yeah, so that's in dot. The black dot is the neighbor order 10, and 1, 2, 3, 4 is how far is the range that gets increased as you increase the neighboring order. Okay, so there should be an exercise just about messing with the neighboring order. There is a few years ago I create a text file that goes through as exercise exactly how this is done. Okay, and how this can be implemented and how it affects the neighbor. I can share that part on the materials for you to actually play with the neighborhood, see what the effect of it is in your simulations. Okay, I'll do that later. Okay, so once you do this, you should get back a well-behaved uh, cell, but it does not divide yet. So let's now implement cell division. Okay, so let's do this. I see that you have already done it. Okay, but let's walk through exactly how this is done. So to add cell division, okay, you probably have already done that before. You have to create a new stepable to add cell division. But now we are dealing with clusters. So instead of using the original cell division plugin, we have to use the cluster uh, division plugin or the ClusterMitosis. So the way you do that, you go back to your tweedit, you right click on the steppable files and should open new options, and you can select the add steppable. Okay, if you have not seen before, this basically adds a new steppable to your files. Okay, so right click on the steppable to edit, click add steppable, and what you should see is a window, a pop-up window that looks like this, where you have to give the name of steppable and you want to select which type of steppable it is. It's usually set up as generic, but this time it's going to be a steppable that implement cluster division. So I want to select ClusterMitosis here and just give a name of the steppable. And my suggested name is going to be divide cluster cell. Right click, add steppables. You get a pop-up window, divide cluster cell and select cluster mitosis. Hit OK. And once you hit OK, you should get first two files were modified on your system. You have the main Python file and the steppable files, so they should both look red. And when you look at the steppable file, you should see this new piece of code and this new class here, divide cluster cell steppable, and that's how it should look like. And so you should see kind of three parts of this one. And the first part is just to show how you can deal with cell cluster on the CompuCell3D, okay? The second part that I highlight in red here is how you decide which cluster you're going to divide or not. And the last cell is actually when you divide the clusters, okay? So I'm going to go through one by one. So again, the first one is just show how you can handle the clusters. So basically here is going over all the cells in your that's in your simulation. And for each cell, you can grab the cluster that belongs to or the list of clusters of cell compartments inside your cluster. So self get cluster cells and you give the cluster ID and I'm gonna give list of all the compartments that are inside your cluster. Okay. And then what you can do, you can loop over all these compartments inside your cluster. So that's what we're doing here. You're going over the list of compartments in your cluster. So you're going over this one, and that one. That's what it's doing. Okay. Now, what's really important is that second part where you're actually gonna go over all your cluster and select and define which one should be dividing or not. So the way that is done, you have a mitosis cluster list ID, which is empty, which is going to be the list of clusters that you divide. And then you get, you're going over all your cluster in your cluster list, okay? And the default is by going over all the cluster cell compartments and seeing and computing the volume of the clusters and then defining if you're going to divide or not based on the volume. But we don't want to do that because we want to add grow. We want to do something more simple. So instead of having a criteria that's based on the cell volume, we're going to replace this with a criteria that's going to be just a random by random chance. So to do that, you're going to substitute this cluster volume bigger than 250 by just kind of check if your random number is less than 0.001. So I want to just replace this comment by this one. But of course, to use random numbers, you have to tell Python to access the random library. So at the top of at the first line of your steppable files or right before you implement the steppables, you want to add the line from random import everything, okay? So make sure that you add this line here from random import everything and substitute this criteria by the random criteria. So your code should look like this, okay? Random less than 0.1, and again, add the from random import everything on the top of the file. And make sure that you add from random import everything on the top. So that's the one change that you have to do, okay? And the last thing I want you to do is when you have the cluster division or subdivision, you always have a update attributes function. So I want you to go there and usually assumes that your division is based on the cell growing and dividing. Here's just kind of is a division that happens out of nothing, okay? So instead of going over all the compartments and divide the target volume by 2, okay, you just kind of get rid of that part and we just clone the clusters because the cells are not growing, dividing. Okay, so you just get rid of those 2 lines. So your update attributes function should just be given by these 2 lines that you have here. Okay, so do that. Okay, so do all these changes. Okay, and that then run the code. Okay, and when you run the code, you may have something. What I expect you to see is exactly what your colleague plays on the chat. If it's something that Kumar had, okay, I do not know how to pronounce your first name, uh, Hagu, yeah, the cells are splitting, okay, so you see the addition of new compartments, but they are still glued together, right? So they are splitting, but they're not splitting, they're still mixed, right? So that's exactly what you should see. Yes, Ali is seeing that now. Aritra is seeing it. Yes. So what you the this kind of failure is exactly what you expect to see in your code. Okay. The cell divides, but does not look nice. Now the question for you: why does not look nice? Why they're still mixed? What are we missing? Okay, Karen, if it's not splitting, make sure that you save all the files in your into it, because when you add the steppables, what happens is that 2 files are created. Okay, well, 2 files are changed. You change both the steppables and the main Python file. Okay, so make sure that they're both saved and blue. Okay, so you should click the save all or click one by one and save and then try again. No, when you do divide by okay, very good question by Leonardo. No, they do not inherit the cluster ID. When you use cluster division, okay, you automatically assign a new cluster ID to the 2 cells. Okay, so that's handled by the player for you. So that's not the issue. The issue is more like what Maisha is saying. They kind of need a repulsion between those different cluster IDs. So Maisha, to implement what you said, what do you have to change the code that we did not change? So any guess what we should doing now? You already assign all the cells to be had the same cluster ID. Now we divide, and they do have different cluster IDs. Okay. Yes, you should go back to the cell contact energies because we did change the internal contact energies, right? And everything was looking fine. But now we have 2 cells, and once you have 2 cells with 2 clusters, now they start to interact with each other through the external contact energy values. But we did not change that. Okay. Yeah. So what you have to do, you have to go back to your XML code and choose appropriate contact energies. Okay, so that's what you have to do in order to have that. Okay, so let's go out back. So let me just walk through the idea here. Um, so we have changed the internal contact energies so it looks like what you see here on the right, but the external contact energy is still the same ones as before, and we have to change that. And now I'll leave that up to you. What values should be? Well, we already said that you have to give high contact energies. My suggestion is to give very high for the nuclei and kind of high for this other one. So I'll let you all choose which numbers you want to put there. So they have to be higher than these ones or they're going to mix. Okay. So give your choice of very high contact energies and let me know if you are able to fix your simulation or not. And if you are to, if you're successful, please share a print screen to everyone in the chat. Aritra got it working. Why is the contact? how does the CompuCell knows that it's taken about different cluster numbers? Because you chose ClusterMitosis on your for your plugin, right? Once it does a ClusterMitosis, it automatically assigns different cluster IDs to the other compartments. So, and because you assign different cluster IDs to the dot compartments, you know that those two crawling cells now have to interact with the external contact energies. So the fact that they have different cluster IDs tells CompuCell to do the interaction to the external contact energies instead of the internal. Does it make sense? Ah, Ali, you should change the external contact energy, so it should be the second one. Okay, so you have the first one that you see there is a contact internal. There's the other one which is contact. Okay, these are the energies that you should change. So you should change everything with the medium. You leave it as it is, but cyto-lamellipodia, cytonucleus, and lamellipodium nucleus, what you have as uh, 11, 10, and 40, or even 5 and 10 is the one that you should change. So basically, one, two, three. Out this, the last six energies is the one that you should change. Oh, very good question by Nathaniel. Uh, in uh, in the external contact energy, you should not delete cytosite lamel pairs because they do exist, right? You do have a cytoplasm next to a cytoplasm of another cell, okay? So they do come in contact, so you should define them and should define them high. If you just remove those ones in the external contact energy, CompuCell will interpret this as having zero energy. So they will like stick with one another. So you have to leave them for sure, okay? In the internal contact, you don't need to define that because you assume that you have one copy of each compartment type inside. So you can skip that. But for the external one, you should have all of them, all the possible pairs. Okay. Shamayita got it. Ali got it. Excellent. So these are the values that I choose. I choose to have 50 between all the different compartments. So they kind of can get close, but they do not mix. And I chose 100, a very high value for the nucleus and everything else, because the nucleus should be all inside the cell. All right. All right. So you're exactly right, Ildis, Robert. In this example was easy. In other examples may not be. So you have to really be careful about exactly how you set the initial condition. And I'm going to show that very quickly in the next exercise. Sometimes you can, maybe you're placing cells in a regional space, so you can tell all the compartments within the regional space should have the same cluster IDs. Or maybe you are doing a cell, an epithelium like that. And in this case, all the compartments at the initial that have the same x axis coordinates should have the same cluster ID. Anita, I'm trying to model subdivision two different types of cells together. Can we do this? Yes, you will be able to do that. Yes. Okay. So I only have now 10 minutes for the last exercise. Uh, so,
If you need to run over a few minutes, it's okay.
okay. But this is something that you'll be seeing that again with Prion Adiapak on the uh, next week. So I think it's okay if you want to just follow the slides, and maybe it's better if you guys just follow the slides on this one. Okay. But if you want to go along, please go along. And all right, start by downloading the code 5.1.2.zip. Okay. And for this exercise, you'll be not doing structural compartments like we did for the Cron cell, but you're going to do um, functional compartments, apical, lateral, and basal, as you see here. And what you want to do something that looks like this. You have multiple cells, apical, lateral and base compartment. You have a ECM below. The base compartments are facing the ECM and the apical compartments are facing the medium, okay? And once you have this, you can then add kind of links between the cells and add kind of active properties to induce apical folding, okay? But that's a topic for next week. So for here, we're gonna just use a create epithelium, use the cell compartments, we're gonna choose the energies that those cell compartments should have. So what we're doing here, you're gonna create a multi-template, adjust cell areas, group cell togethers, and adjust the contact energies, okay? So for this one, you can actually start everything from scratch, okay? So if you want to start from scratch, you can just go to Tweet It, CompuCell3D project, new CompuCell3D project, you click that, okay? And once you click that, you should get your selection wizard. Probably that's gonna, by now, that should be the fifth time that you see the creation wizard, so you should be familiar with that. So please make sure you select Python plus XML. Let's call this tissue folding, okay? And hit continue, okay? Or it can be tissue folding, can be epithelial, two-dimensional epithelial, um, or just epithelial layer. So give a name that you see most appropriate, Python XML, hit continue, and then you should get to this next window. So for here, I want you to do two things. I want to select the X dimension to be 350 and the Y dimension to be 100. And I want to select the X dimension to be periodic. Okay. So do that and hit continue. Is everybody good so far? If so, say yes, so I have a little bit of feedback from you. So 350, 100, periodic on the X. You can leave no flux on the others. You hit continue. And now we go to the cell types window, add apical, lateral, basal, and ECM, these four cell types. Okay, so remember, you have to write the name of the cell. So write apical and hit add, write lateral, hit add, write basal, hit add, and write ECM and hit add. Once you see the four, then here, so you have five cell types, we include the medium, then you can hit continue. Did everybody got here? So I trust everybody got here. Now the next window, you select contact and contact internal. So you already know that this module is going to have a contact internal plugin, volume flex, center of mass and neighbors. Hit there, continue. Then you get the chemical fields. You ignore that, hit continue. One thing that's going to show you is this contact internal contact plugins. It asks you to already choose the values right here and now. I want you to ignore that because you're going to set that later and hit continue. Configuration complete, hit done, and then you got your code done, or you can either to go all the steps or just hit this, or just download this part, okay? And now what I usually leave as an exercise is to try to use the uniform initializer plugin to set up this niche condition, where you have a row of apical cells here, a row of lateral cell types here, and a row of basal ECM types here, and a row of ECM on the bottom. And to do this, you usually need 4 copies of the region code for your uniform initializer, okay? And you run your X from 0 all the way through their simulation from 0 to 350. And for the apical size, you're gonna just run from 49 to 56. So it's gonna from here to here. And you do the same thing, and you only place apical cells here. And you do the same thing for lateral, base, and ECM. Okay, so that's how it should look like. okay? Um, so that's how the code should look like once you implement. You have a region where you only place apical cells, a row where you only place lateral cells, a row where you only place basal cells, and a bigger, fatter row where you only place ECM cells. And here give the width of 35 to be this by this, okay? So that's the idea of how to do, okay? And if you do that, I'm gonna just show how you can already download this implementation 5.1.2. And when you run that, you see this, okay? Uh, Simulation, but that's just not the things more or less will disappear, okay? So what you have to do, you have to make it more stable, right? So that it does not disappear. So you have to go in the code and go to the start function and what you have to do, you have to add a code that's found the cell pairs that are on top of each other and assign them to be the same cluster ID. Okay. Um, so how we do that? Okay, we do that by doing the following. We'll do looper over all the one cell type. So let's go do loop over all the apical cells. Okay. And then once you grab one apical cell, we're gonna do a loop over all the lateral cells, and you check if the cells share the same x coordinate, okay? And if they have the same x coordinate, you assign a cluster ID to that second cell, okay? So in terms of code, that's how it's done, okay? You go over all the apical cells, then you do a second loop of all the lateral cells. If they both cells have the same center of mass, you reassign cell 2 to have the same cluster ID of the first cell that you're looping through, okay? And then you do the same one going over the basal cells. If they match the center of mass, we reassign the cluster ID of the cells, okay? So now when you do this, you should get something that looks like this. Now all the cells have the same cluster ID and they are nicely separated into columns, okay? Does that make sense? So if you want to just download the code ready for that, you can just load 5.1.2c and you already have this part of the code implemented, okay? So you have this, and then you run simulation, but you still, all the energies are set to be 10, okay? So what you have to do now is choose what the internal contact energy should be and what the external contact energies should be, okay? So that is really the important part of this code because everything else is just gonna set up the niche conditions. So right now I want you to all interact and think about it, okay? So here you have now three compartments on one side, two compartments on the other side. You have the ECM below, and you have the medium above, right? And you have the internal contact energies and the external contact energies. And it's a lot of parameters for you to choose, right? So so instead of panicking and seeing what numbers should put there, I want you to reason out what should be the hierarchy of those numbers. Okay, so please tell me right now in the chat. Uh, let's start with the internal contact energies. So the contact energies between apical and lateral, apical basal, and basal lateral. These internal contact energies, they should be high or low. Tell me in the chat. Let's figure out those three here. Any idea? Yeah, they should be have low contact energy between cell layers within the cell. Okay, so yes, to ensure contact. So you want that to be low. So they have to be cohesive. So you want to be energies low. You may make the case that maybe apical and base should be a little bit higher because it should be on the opposite sides of the cell. So maybe this should be medium instead of low, okay? But in general, they should be low. Does make sense? And there's also no cells. There, your cluster does not have a medium or ECM compartment, so you can ignore all those values here, so you don't need to define them. So you can leave them blank or just remove the line in the code, okay? Now let's go to these other values here, apical, apical, lateral, lateral, and basal, basal. Do you need to define those energies or not? Well, they also do not exist because you only have one copy of apical, lateral. So it should be zero or you just do not define, right? Uh, you just can skip. Well, it can be low, okay? In case your cell has two apical compartments or two basal compartments, sometimes you want that, but you don't need to define them. You just can skip them. Now let's go to the other side. Now we already set up what the contact energy should be. Now, what should be the contact energy between apical, apical, lateral, lateral, and basal, basal? Should be low, high, medium, lower than these ones, lower but bigger than this one. What should those three values here be? Arita said also be low. Should they be low as much as these ones? More or less? Okay, Gabriel said lower than these internal ones. Okay. Does everybody agree? Okay. If I make those apical, apical, lateral, lateral, and basal, basal across clusters to be lower than these ones, what will happen is that they'll start to kind of migrate in between them. So actually, you do not want to be lower. You want them to be low, okay? But you want to be low, but slightly higher than these ones. So you cannot, so the cells will not kind of merge with each other, okay? You still want them to be low because you want the apical to be contact with apical, lateral with lateral, and basal with basal. You want them to pair, or okay, with one another. But so they have to be low, but they don't have to be lower than the internal ones. Because if this is lower than these two, what happens that this red cell is gonna go in between those here. Does it make sense? Now let's go to these other ones here. Let's look at the cross terms. This with this one, the lateral with the apical and the basal, and the basal with the lateral and with the other apical. Should those three, which is going to be those three values, should they be low or high? So the cross terms between compartments, sorry, between clusters. Gabriel said that should be higher. Yes, they should be higher because then otherwise you're going to start to misalign, right? If they're low, they start to misalign. You have to couple L, and B, so it's going to be a nice epithelium. So the epithelium do not extrude one side from the other. Okay, so they should be high. And what about basal? Uh, let's look at the apical side. Should the apical side prefers the medium? What's contact energy should be with the medium and DCM? Should they be both high, both low, or should be one high and another low? So should apical and medial be high or low? Okay. What should be the apical and the ECM be? So the apical should never face the ECM, right? So the apical should have a very high energy with the ECM. Do you agree? But it should have a kind of low energy with the medium because you should like that one. Okay. So I say that apical and ECM should be very high because it should never flip and be upside down. So it should prefer to be face the medium. So it should be kind of low, but not too much low here in the medium. It should be very high with DCM. Does that make sense? Okay. If it makes sense, yes. Say yes in the chat. Okay. Now, what should be the energies of the basal and with medium and ECM? They should be the same or they should be inverted. Should basal also have a very high energy with ECM or should have a low energy with ECM? Low energy. And what about with the medium? High, yes. Okay, so it should be reversed here. Okay, and what about lateral with medium ECM? Should be high with one and low with the other. Well, what you choose? Well, the lateral had to be in the middle, right? So it should never come in contact with the medium. It should never be coming in contact with the CM. So say that the lateral one should be, yes, high both, as your colleague said. So yeah, it has to be high both. And what should be the addition between medium and ECM? Okay, medium ECM should be super high, right? So uh, ECM, ECM 0, and ECM with the medium should be super high. So what we did here, okay, we see that we have a lot of numbers to choose from. Some of them in internal, you don't need to specify, so you don't need to worry about them. You know that the cells have to be cohesive, so you have to use them low. And then what you have done here in the external one, you just kind of reason out what they should be. So we did not put numbers right away. What we did, we see, okay, that's the behavior that my cell should be, right? You should couple apical, apical, lateral, lateral, and basal, basal, so they have kind of low energies. They should not cross, or they should have kind of high energy between cells so they remain aligned. And these ones should be on this side, but never on the other side. So you choose low here and high here, and invert it for the basal. And the lateral should be in the center, therefore it should have high energy with both the median and the CM. So that's a very, very important uh, exercise before you blindly put numbers on your addition matrices. You first have to make a hierarchy or what should be high, what should be low, what should be higher or lower than other ones. And once you establish what the hierarchy would be, okay, then then you go ahead and add the numbers on top of that. Okay. So you just not put the numbers blindly, you just look at what the behavior should be, and then you choose the hierarchies, and then you put down the numbers. Does it make sense? So this one a very important exercise, not only for cell compartments, but for using the cellular plots models in general. So you came off the hierarchy, okay? That's how it looks like. And then what you can do, you can choose what numbers to put in, okay? And uh, you can do this exercise in the lunch break, but here is just for you to see what numbers I put. And when I put those numbers that you see here, like say very low here, 2, 5 here, 10 here, 20, when we said that should be very high, okay? That is how the epithelium looks like in my simulation, okay? So does it make sense? So if you want to have a copy of all this implemented, you can just go ahead and download 5.1.2 d.zip and you have all these already implemented with those additional energies. You can choose other additional energies and see if it works better than this, okay? Not saying that this is the best one out there. I would say that it does not feel as well organized as the picture, okay? Check if you actually separate the cells into compartments, okay? You may be missing uh, that part of the code. I know that you went kind of fast there, but you can. But if you download 5.2c, it has everything right set up for you except for the additional energies. So you can try that one. But if you download 5.2D, you should see this. Okay. And now that you have a stable epithelium, you can do other fun stuff on top of that, like adding forces between the apical side and induce apical constriction. Okay. But that you're going to see only next week with Prion. And I'll stop here because I'm already over time and it's time for the flashlightings. If you have more questions, please set in the chat. I hope that this module was useful and that you were able to follow through. I apologize for the mistake in the beginning that kind of eat up over a lot of our time, but I hope that was useful and that was clear. Again, all the slides are saved. All the copy of the exercise are also saved, and you can go back and check them and the exercises. And I'll stop here. If you have any questions, I have to take them. Okay, thank you very much.